first thing we're going to study in gas laws is kinetic molecular theory. So this is a big picture. We're trying to describe what gases are, how they move, and how they behave in a container. And we measure their pressures, their temperatures, their volumes, and how many moles they have. So right now we just want to qualitatively describe and define these. Pressure specifically is the number of collisions not with the other gas particles, but with the container. We're trying to describe the gas as a unit, so how does that whole gas interact with the container? And it does so by pushing out. The gas particles are moving, and if you think about it as each gas as a moving ball, every time they collide with the container, they're going to put a force on it, and that force is the pressure. So they do interact with one another as well, and they give energy to one another, but specifically with the container, we're trying to think about it as a single unit. Temperature is going to give us the average kinetic energy of the gas. And if you remember your physical science or physics, kinetic energy is equal to 1/2 mv squared. So it's proportional to the speed. Sometimes it's easier to say, if we know that the gas particles are moving faster at higher temperatures, really it's the energy that we're measuring. It's the average energy. But it's proportional to the speed, so they're related, and how big the particles are and how much they're moving. Volume is pretty obvious. It's how much space they take up. And moles is how many particles there actually are. So now we start to qualitatively say, how do these things affect one another? If I have more stuff, how's it going to affect the amount of space it takes up? If it's moving with a higher energy or faster, how does that affect the number of collisions? If it takes up less space, how does that affect the number of collisions? So qualitatively, we start to ask these questions to describe how the gases move. Secondly, we're looking at mathematically, how do these properties change in a single gas? And we look at, we get the combined gas law. And this shows us mathematically if the temperature, let's say, gets colder overnight, how would that affect the pressure and volume in your car tires? So mathematically, we can start to look at, we have an initial set of conditions and a final set of conditions, and how can these variables change over time in a single gas, okay, just one single gas, because pressures and volumes and temperatures can change all the time. So we just have to keep track of these properties there. Often we measure gases at a term called STP, standard temperature and pressure. There are numbers in there. Standard temperature for gases is 273 Kelvin, or 0 degrees Celsius, and the standard pressure is atmospheric pressure, so 1 atmosphere. Next, we can still talk about single gases, but just in a single set of conditions, we get a gas constant that relates all of those together, and it's kind of derived from this, but we get the ideal gas law. So now we can predict at any single set of conditions, if I know the pressure of the gas is this, and I know the temperature and how much gas I have, what volume will it occupy? So we can start to narrow in a single variable under a single set of conditions for a single gas. How will it behave? Then we start putting gases together. So mixtures, we're not talking about balanced equations and reactions yet. We're just talking about how do we have a mixture. So if we had helium and neon, I'll choose two noble gases so that there's no confusion. They're not going to react with one another, and I put an and sign instead of a plus sign. What happens is when we have a mixture, the problems can get really wordy because each element can have its own variables. So we have to separate them very carefully. what are the conditions for the helium? Separately, what are the conditions for the neon? And if they're in the separate containers, maybe we sometimes put them into the same container, maybe sometimes we separate them. And we can actually share conditions. Maybe we put them together and we say, okay, what is the total pressure? What is the total volume? What is the total temperature? And if you're paying attention here, it's kind of like this, where you've got the helium has an initial and a final set of conditions, and maybe the neon has an initial and final set of conditions, where you can get combined gas laws for each one, but you have different mixtures, so you got to keep track of what each gas is doing separately in the mixture. Ultimately, the goal of that is to do gas stoichiometry, because the gases are going to react with one another sometimes, and that's going to change the number of moles, it's going to change the pressure and the temperature and the volumes of the container. So if we had, I'll take a balanced equation with all gases, and we can start saying how many moles do we have at the beginning and the end. And if we have the moles, we really have some pressure, temperature, volume information. We have some initial, final information. So we're really interested in how many moles do we have at the end of all of these things, because then they're all going to have their own pressures. They all might be in the same container at a certain volume or temperature, and we need to do some stoichiometry with moles. So that gets us back into the ideal gas law, and we can start changing conditions also. This only works with gases, but if we know their conditions are not changing, we can actually start to do stoichiometry in pressures, because the pressure is proportional actually to the number of moles. If we know that pressure measures collisions, and collisions depend on how much you have, we can actually do some pressures in here and do some stoichiometry with pressures as well. And we can actually do that with volumes because of molar volume, which we'll talk about later. All gases, if they're under the same conditions and the conditions aren't changing, you can start to talk about the volumes of gases reacting with one another too. So you get a little bit of open options with stoichiometry, but that's still the goal, is to say, okay, how much do we have left of everything, beginning and final? And then the gas part is, now what does that tell us about the pressure, temperature, and volume of the gas? So that's chapter 5 in a nutshell, describing at the beginning how gases behave, how can we measure them, individual gases, and then keeping track of them in separate mixtures to ultimately do some stoichiometry and do some chemistry with them.